you can there's certain animals that go through larval stages, right? So you can take, so what the Russians were using beetle larvae, and Doug and other people used moths and butterflies. So what happens is you train the larva, right? So here you've got a caterpillar. So this caterpillar lives in a two-dimensional world. It's a soft-bodied robot. It lives in a two-dimensional world. It eats leaves and so on, right? And so you train this thing for a particular task. Well, during metamorphosis, it needs to become a moth or butterfly, which it lives in a three-dimensional world. Plus, it's a hard-bodied creature, so the controller is completely different, right? For running a caterpillar versus a butterfly. So during that process, what happens is the brain is basically dissolved. So most of the connections are broken, most of the cells are gone, they die. You put together a brand new brain, it self-assembles, and you can ask all sorts of interesting philosophical questions of what it's like to be a creature whose brain is undergoing this massive change. But the information remains. And so one can ask, okay, this is, certainly for computer science, it's amazing to have a memory medium that can survive this radical remodeling and reconstruction. And there's the RNA story, but also you had mentioned, does this work for mammals? So there was a guy in the 70s and 80s. There was a guy named George Ungar who did he's got tons of papers. He reproduced it in rats. So his was fear of the dark, and he actually by establishing this assay and then fractionating their brains and extracting this activity. Now he thought it was a peptide, not RNA. So he ended up with a thing called scotophobin, which turns out to be, I think, an 8-mer peptide or something. And the claim was that you can transfer this scotophobin, you can synthesize it and then transfer it from brain to brain. And that's what he thought it was. And then of course, I think David Glanzman favors RNA again. But yeah, I agree with you. I think that's a super important story of how it is that this kind of information can survive just massive remodeling of the cognitive substrate. In Planaria, what we did, and Planaria, they have a true centralized brain. They have all the same neurotransmitters that we have. They're not a simple organism. What we did was McConnell's first experiments, which is to train them on something, and we train them to recognize a laser etched kind of bumpy pattern on the bottom of the dish, and to recognize that that's where their food was going to be found. So they made this association between this pattern and getting food. And then we cut their heads off, and we took the tails, and the tails sit there for 10 days doing nothing. And then eventually they grow a new brain. And what happens is that information is then imprinted onto the new brain. And then you can recover behavioral, evidence that they remember the information. So that's pretty cool too, because it suggests that, well, we don't know if the information is everywhere or if it's in other places in the peripheral nervous system or in in the nerve core, that we don't know where it is yet. But it's clear that it can move around, that the information can move around in the body, because it can be in the posterior half and then imprinted onto the brain, which actually drives all the behaviors. So thinking about that, I totally agree with that. This is a really important rabbit hole for asking. But there's an interesting puzzle here, which is this. It's one thing to remember things that are evolutionarily adaptive, like fear of the dark and things like this. But imagine, and this hasn't really been done well, but imagine for a moment if we could train them to something that is completely novel. Let's say we train them. 3 yellow light flashes means take a step to your left, otherwise you get shocked, something like that. And let's say they learn to do it. We haven't done this yet, but let's say this could work. One of the big puzzles is going to be when you extract whatever it is that you extract, let's say it's RNA or protein, whatever it is, you stick it into the brain of a recipient host. And in order for that memory to transfer, one of the things that the host has to be able to do is it has to be able to decode it. And in order to decode it, it's one thing if we share the same code book, and by evolution, we could have the same code book for things that come up all the time, like fear of the dark, things like that. But how would the recipient look at a weird sort of, some kind of crazy hairpin RNA structure and look at and analyze it and be like, oh yes, that's 3 light flashes. Mm-hmm. And then step to the left. I see. So you would need to be able to interpret somehow this structure and convert it back to the behavior. And for behaviors that are truly arbitrary, that might be, I don't know actually how that would work. And so I think the frontier of this field is going to be to have a really convincing demonstration of a transfer of a memory that doesn't have a plausible pre-existing shared evolutionary decoding, because otherwise you have a real puzzle as to how the decoding is going to work. So this idea, and then even without the transfer, you can also think of it a different way. Every memory is like a message, is like basically a transplanted message from your past self to your future self, meaning that you still have to decode your memories. Whatever your memories are, in an important sense, you have to, those engrams, you have to decode them somehow. So that whole issue of encoding and decoding whatever the substrate of memory is maybe one of the most important questions there are.
You just watched a clip from the Theories of Everything channel. For the full video in all its magnificence, then click here. And if you'd like to see more, then subscribe. Enjoy. If you enjoyed that clip, then the full podcast is out right now. You can click around here. Enjoy. Subscribe to Theories of Everything to get notified of upcoming podcasts, as there are new full-length podcasts every week on the topics of mathematics, physics, consciousness, free will, and AI.